Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Hydrostatic Fluid Mechanics Applications and Such. As always, please be an attentive learner while watching this video. By way of introduction to fluid pressure and fluid force. Swimmers know that the deeper an object is submerged in a fluid, the greater is the pressure on the object. Pressure is defined as the force per unit area, that's like F over A, over the surface of a body. For example, because a column of water that is 10 feet in height and 1 inch square weighs 4.3 pounds, the fluid pressure at a depth of 10 feet of water is 4.3 pounds per square inch. Now this asterisk does make reference to the fact that the total pressure on an object in 10 feet of water would also include the atmospheric pressure, the air that's above you, due to the Earth's atmosphere. And at sea level, this atmospheric pressure is approximately 14.7 pounds per square inch. Now, since this pressure is everywhere, often in these problems it will be ignored, so it doesn't have to be included. But from a purist standpoint, you do want to acknowledge that this exists, and we've done that now. Okay, so we figured out it would be at 10 feet, it would be 4.3 pounds per square inch. At 20 feet, this increases to 4.86 pounds per square inch. And in general, the pressure is proportional to the depth of the object in the fluid. So, the pressure on an object at a depth h in a liquid is pressure is equal to W times h, where W is the weight density of the fluid per unit volume. Now this is volume, like maybe pounds per cubic foot, but then you're multiplying by feet, and so you get pressure is force per square unit, or force per area. Okay, below are some common weight densities of fluids in pounds per cubic foot, and you see that alcohol and gasoline are light, as is kerosene. Mercury is very heavy. Seawater has some salt in it, so it's a little denser than regular pure water, and so on and so forth. Now, although in the real world the nature of the fluid is very significant, and we do have to acknowledge if I'm in seawater or some other fluid, for assessment problems in this class, I often will just say the weight density is W, in which case the answer will have a W in it, and I do that to simplify your calculations just for assessment purposes. When calculating fluid pressure, you can use, and we will use, an important and rather surprising physical law called Pascal's principle. And this is named after Blaise Pascal. Pascal's principle states that the pressure exerted by a fluid at a depth of h is transmitted equally in all directions. So for example, in this picture, the pressure at the indicated depth is the same for all three objects. So you see here you have a vertical one, you're at a depth h. The pressure happening there is the same as the pressure happening here, even though this is oriented differently, or this with a different orientation, the pressure is the same. So that's Pascal's principle. And so it's the same for all three of those. It depends only on the depth. And because the fluid pressure is given in terms of force per unit area, P equals F, force per unit area, the fluid force on the submerged surface of area A is, the fluid force is P times A. You just multiply both sides of this equation by A, and that is pressure times area. And so pressure times area is the fluid force at that depth. Let's look at an example. So here, and I do let you see the picture, find the fluid force, that's the force down here, on the rectangular metal sheet measuring 3 feet by 4 feet that is submerged in 6 feet of water. So the surface of the water is up here, you submerge it and it's down there, and that's the picture. Okay, you know what to do. Let's see how you did. Okay, now this was water, and since the weight density of water is 62.4 pounds per cubic feet, and the sheet is submerged in 6 feet of water, the fluid pressure is, now this is pressure is equal to the weight density times the depth. So the weight density was 62.4, and that is pounds per cubic foot, and this is 6 feet, so you see the cubic feet become feet squared. So this is, when you do the multiplication, these are the units. It is pounds per square foot. So that is the pressure at that depth. And by the way, everything is at 6 feet. There's no change in depth. So because the total area of the sheet is 3 times 4 is 12 square feet, the fluid pressure is, now the fluid force, excuse me, the force is F is equal to P times A. Well, this was P times A. The square feet will cancel out and you will get pounds, and you do the multiplication and you get this number. And notice that this result is independent of the size of the body of water. The fluid force could be the same in a small swimming pool in someone's backyard or in a big lake like Lake Michigan. It only depends on the depth. In example 1, the fact that the sheet is rectangular and horizontal means you do not need the methods of calculus to solve the problem. All we were doing was multiplying a bunch of numbers. But now we're going to consider a surface that is submerged vertically in the fluid. So here is a piece that we're putting, but we're submerging it vertically. Now you see the bottom of this is at a different depth than the top of this, and so we're going to have to use calculus to do this problem, and this is the kind of problem I'm probably going to ask you. This problem is more difficult because the pressure is not constant over the surface. I already said that, I think. So suppose a vertical plate is submerged in a fluid with weight density W. Now notice we are using W now for that, as shown in the picture. So here's the fluid, you're submerging it, and so forth. By the way, part of the engineering and physics tradecraft is in selecting an appropriate coordinate system. This is your choice, but some selections make the problem and computations easier. This comes with experience. As always, you should do a bunch of problems. Okay, so anyway, we've got this submerged. So to determine the total force against one side of the region from a depth C to a depth D, so we're talking about changing from C to D, you subdivide the interval CD, so this whole thing is CD, I guess, into n subintervals, and this is a little subinterval that we're dividing it into. Next, consider a representative rectangle of width delta y. So you see we're picking, this is our y-axis, and this is delta y, so that's that little piece that you're doing there. That's the width of the piece is delta y. And the length of the piece is L of y, where L of y is the distance from this side of the rectangle to this side of the rectangle. So you see this is going to be length, and that's going to be a length. And so that's length, and length is length squared, but then we're going to have a depth, which is also length. And so you're going to be cubed there. So anyway, here we go. Next, consider that representative rectangle, a width of delta y, a length of L sub yi, where yi is in the ith subinterval. So the force is going to be equal to the density times the depth times the area. So the area is going to be L of y, that's this dimension, times delta y, which is this dimension, that's area, and then you take this times W, weight density, times h of y, because h of y is how far down we're going. So the force against n such rectangles, because we're slicing it into all these little rectangles, is you just add them up and you get this. Now, W is considered to be constant across all that because it's a homogeneous fluid and is factored out of the sum, so we get this. Therefore, when we take the limit as, and this is fancy lingo about n going to infinity, and the length of the smallest, of the largest rather, rectangle goes to 0, then we find that, oh, that's just W times the integral from C to D. It started at C and we went up to D. That's actually supposed to be a D there. So you integrate in the limit, and this is h of y, L of y, and L of y is the cross section this way, dy, where h of y is the depth of the fluid at y, so that's what we have there, and it is a function. And L of y is the horizontal length, that stands for length, the L stands for length of the region at y. So this is a very good picture, and this is the definition, and we're going to use this formula over and over again. Let's do an example now. So this is fluid first on a vertical surface. So and you can see this is a very applied problem. A vertical gate in a dam, so here's a dam, this is the vertical gate, has the shape of an isosceles trapezoid. Now, isosceles trapezoid means that this side is the same length as that side. That means that the non-parallel sides are the same length. That means it's isosceles. 8 feet across the top, so it's 8 feet there, and it's 6 feet across the bottom. And the height is 5 feet. Now, the height is the perpendicular here, so it's 5 feet from base to base is what that really is saying. As shown in the figure, there's the picture. But the question you have to ask as an engineer is, how strong do you have to make the gate? And so you have to say, what is the fluid force on the gate when the top of the gate is 4 feet below the surface of the water? So you see the water's up here, there's the water, and you're 4 feet below it is where that is. So there is force. Now, the force is different down here than it is up here, so this is a calculus problem. You should know what to do. Let's see how you did. Now, we are at liberty to pick our coordinate system any way we want, so we're choosing to pick our coordinate system like this. So this is the x-axis, that is the y-axis, and this is a picture that we have. And when we pick this coordinate system, because we know it was 8 feet across here, and it was 5 feet further down, it was 6 feet across there, I can assign coordinates to all this stuff. So this is the point 4, minus 4. This is 3 minus 9. And this slope is the negative of this slope, and so all that stuff makes sense. This is important. Your picture matters a great deal, so you need to spend time doing that. Okay, so we set that up that way, and that means the depth is going to be equal to h of y, and that's going to be minus y. Now you might say, well, why is it minus y? Well, let's suppose we go down to minus 9. If you're at minus 9, the depth is not minus 9, it's minus a minus 9. So h of y in this case is minus y because of the way you set up the coordinate system. And we're going to want to understand this line here. And so, but we know 2 points, so we know the slope, and we can find the intercept, so we can use the slope-intercept form, this point and this point. And also what we're going to see is the distance from here to here is the same as the distance from here to here. So the distance from here to here is going to be x. You want to think about this picture a great deal. Okay, so the equation of this line is y minus the y coordinate is equal to the slope. This is the slope. Minus 4 minus a minus 9 all over 4 minus 3. That ends up to be 5 when you do the calculation. So this is y plus 9 is equal to, and this is 5 times x minus 3. So that means y is equal to, I'm distributing and simplifying and putting it in slope-intercept form, y is equal to 5x minus 24. But I want to know what x is because I need to know this L of y through there. So I'm going to solve for x. So if I solve this equation for x, I have x is equal to y plus 24 over 5. And the length across here, the way I set up the coordinate system, is 2 times x. So that is 2 times this, or 2 over 5, parentheses, y plus 24. That's L of y. We got that from the geometry of the system. Now we're going to integrate from y equal minus 9 to y equal minus 4, because you see that's where we go. This one is at minus 9, this one is at minus 4. So we're integrating across there, and so this is going to be, the force is equal to W. Remember that factored out. I integrate from minus 9 to minus 4. H of y is minus y in my coordinate system. And then I have to put L of y, dy. Now I'm just going to pause here, but you see you certainly can pull out the 2 over 5 and distribute the y and do the calculation. Actually, I pull out a minus sign, minus 2 over 5. And then this is a pretty easy integral to do. You add 1 to the exponent and divide by the new exponent. You plug in the numbers, and you'll get 13,963 pounds. Now, again, you get to pick the coordinate system any way you want, but this was a good way to do in this problem. Here's another example. I want to determine the hydrostatic force on the following triangular plate that is submerged in water as shown. So you see this is the level of the water. So we're up there. This is 6 here, and the triangle goes down like that. Again, some geometry is involved. You know what to do. Let's see how you did. Okay, now what we're going to end up doing is this is our representative slice. And here, just because it doesn't matter, I am going to pick this to be called x. So the distance down to the slice is called, this particular slice is called x. And since the whole distance was down 4, this distance is going to be 4 minus x. So this one I'm calling x, this is 4 minus x. And this variable across here is I guess if I'm calling this x, I should call that y. Okay, and the strip is, this is going delta x, so that's the change in height. The width is 2a because I'm going from there to there, so I have to figure out what that a is, but notice that a changes. A is 0 up here, and it becomes 3 up here. So that means I need to know the equation of this line. Now I'm going to figure this out using similar triangles. So you see the big triangle has 3 is to 4 as a is to 4 minus x. I'm writing that over here. So 3 is to 4 as a is to 4 minus x. And I can solve for a. And if I do, I get that a is equal to 3 minus 3 over 4x. And you want to do that, you cross multiply and solve for a. Okay, so that is going to be what this is. And then I start doing this. Now, we're actually doing a lot of the calculations here. So rho is the density with mass, g is the acceleration due to gravity. That makes that into a force, and times d, and d is the depth that we are at. And so when you figure that out, the depth is going to be x in my little story. There's x, I. And so if you multiply all those numbers together, you get this. And so the force is the pressure in that little slice times a. So that is going to be 2a. You see, you get 2a because you go from a to a the way I chose the coordinate system. Delta x. So this is going to be that number times 2. This is what I found a to be, and that's delta x. So when I simplify that a little bit, I have this. So in that rectangle then, what I'm going to have is this is going to be the force in that rectangle. And if I add up all those little rectangles, I get something that looks like this. But if we take the limit, as n goes to infinity, the sum becomes an integral, and so I'm going from 0 to 4. Now that means I'm calling this 0 and this a positive 4. Again, we're choosing a coordinate system differently here. You could choose a different one, you should get the same answer. So we're going from 0 to 4, And this is going to be, I'm going to distribute that x, so that is 3x minus 3 over 4x squared dx. So I distributed that. This is actually a pretty easy integral to do. You add 1 to the exponent, divide by the new exponent, plug in numbers, and you get 156,960. And the units here have to be newtons because apparently those were meters in the statement of the problem. Similar triangles are often important things for engineers. Here's another problem. Find the hydrostatic force on a circular plate of radius 2 that is submerged 6 meters, that's 18 feet, in the water. You could think about this as a porthole on a submarine, perhaps, that was submerged that low. You know what to do. Let's see how you did. Okay, here's the picture that we're going to be using. Now, and there's a little bit of interpretation required. So the submerging 6, let's see, what are these, 6 meters, says that the top of the porthole is 6 meters. So this distance is 6. But you see, we're going to be adding up these slices. So what we're going to do, we need a coordinate system, and we're going to pick a coordinate system that is down here at the center of the circle. Again, I'm showing you different coordinate systems. So we're going to be there. So now we're going to call this y sub I. That's going to be the distance from the middle. And the distance across here is going to be, this cross section is, you're cutting the porthole, and the equation of the circle, because this is a circular portal, is x squared plus y squared, because we're choosing this to be 0, 0. X squared plus y squared is equal to 4. Okay, so that's the equation, and that means if I solve for x, which is going this way, x is equal to the square root of 4 minus y sub I squared. Now that's for this little bitty rectangle that I have here. Okay, so that's the picture that we're setting things up, and you see the surface is up here, so the distance from here to here really depends on the radius of the circle. So this distance is d, and so that's going to be 6 plus, and then I go down here, and this is going to be 6 minus y. We'll look at that. So anyway, we have this strip, and that's what we're going to do. So the depth below the wattle surface for each is d sub I is equal to 8 minus y sub I. Now, clearly here, you can say, oh, this depth of this is d minus y sub I. But it's also true down here, because you might say, well, it's d plus that. Yes, but this has a minus y coordinate because I'm picking my center here. So you see, this is true for everything within the circle. And in turn, the pressure on the strip then is going to be, and again, we're going to be doing that work with the acceleration due to gravity and the density of water and so on and so forth. We're going to get this, and then this is times. So the pressure on that little slice is this number times 8 minus y. Okay, so here we are. This is a bigger picture, but we've got that, and those are most of the things that we said. So the area is going to be L of y from here to here, but that's 2 times from here to here. So that's going to be 2 times that, and then that is also delta y, because what we're doing is this is delta y, is that little height there. Okay, so the hydrostatic force is the pressure times the area. It's that number times the depth times the area. So the force is going to be the limit of that sum, and that's going to be the integral. We can pull out the constants, but you're going from minus 2 to 2. Now we're taking this to be at 0, 0, so this means this is minus 2, this is minus 2. We're integrating dy. So we go from minus 2 to 2. For every place, this is 8 minus y, and this is the square root of 4 minus y squared dy. You really need to think about this. You might want to pause, draw pictures, and make sure you're getting this, because one day you will be setting these up for a problem. So this is the integral that we need to do. So we're going to split this into 2 integrals. It's going to be 8 times this business minus y times this. Now, this integral here, the second integral, is pretty easy to do. It's a y substitution because I have a y up there, so I'm going to let y equal 4 minus y squared excuse me, u equal 4 minus y squared, but I have a y there that's going to help me, and that's dy. So that integral is pretty easy to evaluate, and you should be able to evaluate. This one's a little harder. This is 8, and this is 4 minus y squared. Now, we've done trig substitution, so that's a trig substitution. And when you do the trig substitution and work through everything, and you should work through it, you use the trig substitution y equal to sine theta. Then this becomes the second integral. Well, this is the second integral, becomes that after you do the substitution of v is equal to 4 minus y squared. You get this. This goes, by the way, from 0 to 0, so that's actually going to be 0 contribution. But the other one is going to end up with the trig substitution. It's going to be cosine squared theta d theta. You should work these details. And since this is d theta, we have to have theta for our limits. This goes from minus pi over 2 to pi over 2. And to integrate a cosine squared, you remember that we have to use the double angle formula. This is 1 plus cosine 2 theta. Because that's the way we do that. We get this, we plug in the numbers, and we get this. Now, I'm going to let you do one yourself. Here's a circular observation window. It's down here. Now, we're using a little bit different thing. The ship this time, or excuse me, the window has a radius this time of 1 foot, and the center of the window is 8 feet. And they're telling you the center of the window is 8 feet below water level, and here's a picture. And they are helping you because they're giving you kind of a coordinate system for you to help. But the question is, what's the fluid force on the window? It's the same question I was asking before. You know what to do. Let's see how you did. Okay, the depth is going to be 8 minus y. They already did that. And since we chose this to be 0, 0 again, it's 8 minus y even if it's underneath here for the whole thing. So again, it is 8 minus y. Now the length is going to be the distance from here to here. Actually, the L of y is going to be twice that, but this is again a circle. And it was radius 1, so that is going to be, the length is going to be 2x, but that is going to be 2, the square root of 1 minus y squared, because it's a circle. That is the L of y. And we're just letting this be w here. We're not worrying about all those numbers. Or maybe we are. Let's see. Oh, we're using 64 feet per cubic inch, so that's what the w ends up being. We're integrating from c to d. That's from minus 1 to 1 because this is the center. The circle is radius 1, so you go up 1 and you go down 1. So you're going to be integrating from minus 1 to 1. H of y is 8 minus y. This is 2 times the square root of 1 minus y squared. Now, again, you've got to use either trig substitution, or you might say that the square root of 1 minus y squared, you might realize that that's going to be 1/4 of a circle when you look at this. And so that's going to be, instead of being that's going to be, the area of the circle is pi r squared, so the area of the circle is going to be pi. So, actually we go from minus 1 to 1, and so that means we're doing half of that, so that's pi over 2, and this you just do a u substitution. You should check that, but you get the exact answer is 512 pi, and if you round things off you get this. So that is the fluid force on this window. Now this is called to be a capstone, but this is a problem that I have asked on exams before. 2 identical semicircular windows are placed at the same depth in a vertical wall of an aquarium. So this is a window and this is a window. Which is subjected to the greater fluid force? And not only guessing the one on the left or the one on the right, or the one on the right and one over left, I'm asking you to explain your answer. You know what to do. And we're not going to talk about that, but you should ponder that. In closing, now more than ever, time is precious. Each day must count. Do the math that will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.